Welcome to Chapter 3 of my Computer Forensics and Investigation videos. This is covering the Guide to Computer Forensics and Investigation, 5th edition. We're covering Chapter 3, Data Acquisition. So what does that mean by data acquisition? Data acquisition actually is how you obtain data, how you obtain facts, things of that nature. So we're going to be looking at different types of digital evidence storage formats. I explained the best type of techniques for acquiring that data, describe some contingency plans for data acquisition, and explain some basic acquisition tools. Again, this is not a 100% complete overview. This is more of a let's get your feet wet, get some basic core concepts down, and go from there. We also have to look at how we validate, and that includes things like understanding how RAID works, how to acquire data from RAID, how to use remote network acquisition tools, and other tools for data acquisition, which that was funny because that's on both objectives. So let's understand some storage formats for digital evidence. So there are three main format types. We have a raw format, we have a proprietary format, and we have an advanced forensics format. These are the three common formats that people can interact with. So what's raw? What do we mean by proprietary? What do we mean by advanced forensics? So raw formats make it possible to write bitstream data to a file. Bitstream we talked about in Chapter 1. That way we can actually have a 100% copy. The nice advantages of raw formats is it's a fast data transfer, it ignores mere data read errors, and most computer forensics tools can read that raw format. The big thing here is it ignores minor data read errors and just kind of bypasses them or clones them. Really good example was like Clone CD back in early 2000s. When you tried making a copy of a copyrighted disc, it would actually give you a lot of read errors because you weren't allowed to copy it. So Clone CD would actually burn through it. It may take longer to go through all of the read errors, but it would make a one-to-one copy. Disadvantages for raw format: it does require a lot more storage. So if you have a 4 gigabyte disk, the raw format may be quite larger than that. And the tools might not collect marginal or bad sectors. So there's some issues there. Minor read errors, okay, but bad sectors, not so much. So the next one is proprietary format. So a lot of the tools have their own unique formats that are only open by their software. So some of these features could be a compression based off of their algorithms, things of that nature. But sometimes that means you have to have their software, and that's kind of a pain. My background is in EnCase, and some of their file formats are proprietary. So understanding that if I'm working with an EnCase file, I always have to be working with EnCase for those files. So if we're talking about just general image type extensions, we could be, again, compressed or not compressed. Some software can split larger files into smaller segments. They can integrate metadata into the image files. Okay, these are all generic, very broad terms. That's always really funny. The main disadvantage is when you use a specific tool, you may be limited to using that specific tool. The expert witness format is an unofficial standard. I've heard, yeah, I don't know if that is 100% accurate. I have heard several people say yes and several people say no. But that's just one of the things that is out there. That's one that you might want to learn. We have the advanced forensics format, which is an open source acquisition format, meaning you should be able to get the tools. It shouldn't be overly expensive. The design goals here were to provide compressed or uncompressed image files, not to restrict disk image files or disk image file size, provide the space in the image file or to segment files for metadata. It has a lot simpler design. It's actually has a lot more, I don't want to say scalable, but it works with a lot more programs. And because it is open source, it's also multi-platform, so that's been kind of nice. Another big thing that I liked about the advanced forensics format was the internal consistency check for self-authentication. That was a big one. The internal consistency checking was really important. File extensions include the AFD, that's a segmented image file, and AFM, and that's for metadata. Again, you have to remember that the AFF is open source. It works on multi-platform. So that's an important feature for this. So now that we understand a few of the formats, we have to discuss the best method for acquisition. And what's really funny, I'm sorry, but the best really is not the best way to say that. The best way is going to depend on circumstance. So keep that in mind. So there are different types of acquisitions. There's a static acquisition and a live acquisition. Live acquisition is the unit's live, static one, obviously it's not. There are different methods for the actual data collection process. Because again, we're making a bitstream copy. We do not want to work with the original. We want to work with at least one copy. Preferably when we do this, we make 2 copies. So the methods are a disk to image, a disk to disk, a local disk to disk, or disk to data type file, or a sparse data copy of files and folders. Depending on the circumstance for our investigation will dictate kind of which way we go. For example, if we're trying to recover deleted items, this whole sparse data copies of files and folders may not work, because again, the files could be anywhere on the hard drive. So, got to keep that in mind. So, creating a disk to image file, this is a very common method. It's very flexible. That way, again, you can clone out more than one copy. It's a bit-for-bit replication of the original drive. You're going to notice we've been using things like ProDiscover and the FTK. I've also used EnCase. These are good disk to image. That way, we're working with an image file that's a little bit easier to work with. The disk to disk isn't bad, it's just not always the best. So when disk to image copy is not possible, we can always go back to disk to disk. Tools can be adjusted for disk geometry configuration, the layout of the disk. And here again, we're using EnCase. You're going to notice EnCase is going to be popping up a lot, because EnCase is one of the more premier forensics type tools. It's way in depth. It covers a lot of items. It's a great tool. It's just not cheap. So logical acquisition or sparse acquisition. They can take several hours. So when your time is limited, we have to choose the appropriate option. Logical acquisition captures only specific files of interests. Sparse acquisition collects fragments of unallocated or deleted data. So if we're trying to recover deleted items, sparse will probably be the option. If we're trying to just capture folders that we already have evidence in, a logical acquisition is probably more appropriate. Gotta be looking at the disk size, because this is going to matter. Also, are there different data types that are going to have some specific requirements, like a RAID or MEL database files, PSTs or OSTs, which is really funny because an OST is a newer version of a PST. They do more, but yeah. So let's talk about when we make a copy. What are some of our considerations? First of all, how large is the data that we're working with? You have to realize that. Again, if we're working with a 4-disk hard drive image, and we try sticking on a 4-disk image, well, it may work, but realistically, as we go to make that copy, it will probably be inflated, so it probably won't be 4 gigs. So the size of our source and the size of the destination are important. When we're doing the size of the source disk, if we're doing a complete bit-to-bit copy, are we using any lossless compression? Could we compress any of it? Would we want to compress any of it? So we've got to be careful with that. Also, we have to validate it. We validate it through verification of digital signatures or hash values. So when we work with large drives, an alternative to using a drive could be just a tape backup, which that's a little bit weirder, but I've seen that done. Our goal is to, again, retain the original disk when possible. And copies. We work off of copies. So let's talk about contingency planning for image acquisition. Well, we make a copy. Well, we return the original. We do our backup. We do our investigation from that copy. What happens if that copy is damaged? So that's actually why we create duplicate copies of that file. That way we have our backup that we're working on, and we may have a second backup or a third backup. That way, we have a backup just in case. We always want to have at least 2 images for digital evidence. When we do a backup, we actually want to protect, or we actually want to do a bit by bit copy or bit stream copy. We want to have all of it. So we want to be able to copy the host protected area of a disk, as well as any of the data portions of the disk platter as well. So when we go to do this, we may have to have a hardware acquisition tool. That way we can access the drive at a BIOS level, so a low level. So we need to be prepared to deal with encrypted drives. Oh god, this is a big one, especially lately. Whole disk encryption is built into modern day operating systems, things like BitLocker for using Windows, and this makes static acquisitions more difficult. You may have to have a decryption key, or you may have to find a way to bypass the encryption, which is not always easier said than done. The issue here is with encryption becoming so popular and so easy, whole disk encryption is becoming more and more of a hindrance. But again, there's still ways to bypass it. We just have to be diligent within our data recovery and staying on top of our training. Other acquisitions, tools specifically for Windows. The nice thing here is, because we're talking specifically about Windows, some of the advantages is Windows is mainstream, so you should be able to get a lot of tools. This allows making or acquiring evidence a lot more convenient. If we're using a PC, we could do a hot swappable device, a USB dock, for example. Some of the disadvantages is being able to protect the acquired data with a well-tested write blocker. I don't know why that's a disadvantage. We'd be doing that anyway. We want to make sure that we're not modifying the original drive. We want to verify that we are making 100% cloned copy, a bit by bit or a bit stream copy, without manipulating any of the source drive. There are some tools out there that cannot acquire data from a disk's host protected area, hence having the appropriate write blocking hardware so that we can make a cloned disk. Some countries haven't accepted the use of write blocking devices. Luckily the US has, but not all countries have. So that's something that we want to keep in mind. So that was a bit for Windows. So we also have these Mini-WinFE boot CDs or boot drives. Doesn't have to be a CD. It's going to be more of a live disk or a boot disk that will enable you to build a Windows Forensics boot drive. So that way we can mount it and we can load off of it. So before booting a suspect's computer, we could actually connect our drive and then boot to it to clone the suspect's hard drive. So again, there's lots of different ways. So how can we verify that this Mini-WinFE boot CD or this boot drive is actually going to be able to do the right blocking that we need? That's a big thing, is how do we verify? And so what I've suggested in the past is, in your lab environment, we test it. These are common practices. There's a Windows, there's a Mini-PE or PX environment, there's also a Linux environment. So there's different environments to do the same thing. Linux can access a drive that isn't mounted. So that's the thing that a lot of people don't realize. A lot of people think you have to mount the drive in order to access the drive, but Linux has a way to do that. Windows OS's and newer Linux machines automatically mount and access a drive, but you can get a specialized Linux forensics tool that doesn't access media automatically. That, again, eliminates the need for a write blocker, because we're not accessing the drive at all. So that's kind of interesting. So using our Linux Live CD, we can also gain access to the additional forensics tools that are on it. And you'll notice in Chapter 3 in our lab environment, we're going to be going through a few of the different Linux tools so that we can actually show kind of what they are. So one of our lab is actually going to be kind of going through some of them. For online, for obviously you guys may not be doing the labs with us, we have a few well-defined disks. We have things like Kane, Kali Linux can do it, Canopsys. SANS has an investigative toolkit. So there are actually several tools that are out there. Surprisingly, Kali is very flexible. A lot of people associate Kali with just things like ethical hacking, but Kali has an in-depth forensics toolkit built in. So let's go ahead and talk about, if we're dealing with Linux, how can we access things like FAT and NTFS, which are more native file systems or partition styles for Windows? So surprisingly, in Linux, the more current distros can actually access and create both FAT and NTFS partition tables. You can actually also do a lot of the fdisk commands that, again, create, delete, and verify partitions in Linux for Windows. We also have the appropriate make disk commands in MS-DOS, which again allows us to format a FAT file system from Linux. So you'll actually be surprised how many tools are built into Linux to work with or work around Windows-type machines. If we are following the steps, we can go to page 99 in our book to help prepare a target drive for acquisition using our software. So acquiring data with DD in Linux, DD is data dump, it's a command. We can read and write we can read and write from the media device and data files as we walk through our labs. Some of the disadvantages of DD is you have to be a little bit more skilled than an average user, and there is no data compression. You can do a DD with split commands, so we can actually split the data into several volumes, so that's kind of nice. But again, you have to have more skills than the average user. You can see that if you're following along in our book, if we're on page 104, we can actually follow the steps using DD to acquire a disk image with DD from an NTFS disk on a FAT32 type disk. Acquiring the data, again, we have different types of commands, things like dcfldd, so that we can use this as a data management type tool. Though this wasn't really designed for a forensics acquisition, it's still done more often than you'd think. So acquiring data with the appropriate dcfldd type command, it has a lot more functionality. You can specify hex patterns or text for clearing disk space, log errors, look at several hashing options for disk verification. We could be looking at this for status displays, indicating the progress of an acquisition. So this was a big one where we did we did a cheaper tool. We turned it on and it acquired the data that we wanted, but there was no progress bar. So it was just literally, we had to wait, and we didn't know its progress. We just sat there, let it ran, and it ran for several hours, but don't underestimate the importance of a progress bar. Natively split data acquisition into segments, so that was a really good item. And again, verify acquired data with original data or the original disk. We can do that through hashing or other verification process. But we want to make sure that we're getting is a copy. Now that we're done with some of the boot type disks in Windows and the PX environment in Linux, let's talk about using some tools that we've been working with in the lab. Things like ProDiscover Basic. So how do we capture an image? Again, these are more general items. So we would connect the suspect's drive to our workstation, would document, again, the chain of evidence. We would remove the drive from the suspect's computer, configure the suspect's drive as required, connect it to a write blocker because we don't want to modify it, create a storage folder or a working case for our evidence, and we would start acquiring it. We're using ProDiscover proprietary acquisition format, so we can actually go to our book, page 108, to start the ProDiscover basic configuration for acquisition. Again, this is going to be one of our labs, which is the videos for those are coming shortly, just not quite ready for them yet. So capturing an image with ProDiscover is pretty basic. You can follow the on-screen prompts and go from there. The ProDiscover does create image files with a .eve extension. There's also a log extension and a inventory extension. So you want to be able to understand what the extensions are so that you know what programs are going to be working with them. If the compression option was selected, then we're going to use a CMP rather than an EVE. Why they do such a drastic change in extension, I'm not quite sure, but that's what they decided to do. Here we have our ProDiscover basic split image file. So we can actually take an image and split it based off of our requirements. Here we have the size of the original disk, which is about 6 gigs, roughly. And if we're dealing with smaller media, we may have to split that into 3 2-gig chunks, for example. Here we're dealing with the actual capturing of an image. So we would actually, its source, its destination. The destination is extremely important. That's going to be our working area. We can also choose things like its image format. If we're doing some type of case number or image number, we can document it. And we also have the ability to do a description and a password. Depending on your work environment, password may or may not be necessary, but I've always found that putting in a specific description helps. That way when you come back to this, you don't have to guess. It's there, it's simple, it's easy. No having to remember, oh, what case was that for? What was I doing? We can use ProDiscovery. It does have a raw acquisition format. We've already discussed raw. The raw format creates a log file, PDS. Again, why they do the log files that they do, not quite sure. The important part here, using ProDiscovery Basic, the raw acquisition saves only the image data and hash values. It does generate logs, but if we're talking just what it is going to collect or save, images and hash values. We've also been working with AccessData's FTK Imager. We've installed it, but we really haven't done anything to it. This is part of the AccessData Forensics Toolkit. It's designed for viewing evidence disks, and it's also designed to work with disk-to-image files. It also makes them. Evidence drives have a hardware-written blocker device, or you can run it from a live or a mini PX environment. So again, you're going to keep noticing the write blocker is going to be huge here. We have to make sure we're not modifying the original data. We're only working off of clones. They really love their screenshots and the PowerPoints. Here is a screenshot of AccessData FTK Imager. Not sure kind of if this helps anyone, but yeah. So the FTK Imager can't acquire a drive's host protected area, so it doesn't do low level. We need to use a write blocker device and follow the appropriate steps. Boot Windows, connect our drive, connect the target, start the imager, create a disk image. So here we have, again, we select the appropriate drive. We select the appropriate image type. We enter the appropriate evidence information. If we're having a case, evidence number, a description, who's doing it, and notes. So what's the difference between a unique description and notes? Description could be kind of more of what the item is. Notes are going to be kind of what you've done. I've seen this done several different ways, so this is more of a just kind of how you'd like to do it. But you, again, would probably want to verify that you're doing everything according to your policies and procedures within your organization or within your circumstances. So here we're looking at the select the image destination. If we're capturing the image, we want to make sure that we're putting the image in the correct location. We could do things like encryption as well there. Then we have the create image process, and we also have an image summary if we want to use it. Give it time, and it will complete. Has a progress bar and a elapsed time. So how do we validate it? We validate it using hashes. So this means that you have to understand some basic hashing algorithms, and you have to understand some hashing algorithm utilities. Validating is one of the most critical components in forensics. If we make a copy of something, how do we make sure that we made a true one-to-one copy or a bitstream copy? We do that by comparing the hashes. Linux has its specific validation methods. You can again use MD5 sum or a SHA-1 utility. You can validate using the DCFLDD type tool. Again, MD or SHA type hashes, hash log, or the VF, the verify file option. So there's lots of tools built into Linux for validating the appropriate hashes. You're going to notice that MD and SHA are going to be the common ones. There's more out there, but they're the most common ones. Windows has no built-in hashing algorithm, so we have to get a third-party tool. Normally this means some type of commercial computer forensics program that will have that built-in tool. Raw format images do not contain metadata, so that's more of just an FYI. We can separate manual validations. If we're dealing with raw, they normally do say separate manual validations, just so it's a little bit better, a little bit quicker. This is where it starts getting interesting. Performing RAID data acquisition. Because RAID could have parity, could be mirroring, could be striping. Size is a huge concern. Terabytes of data. Now this is where you can tell this is kind of old. We actually just deployed one server that had, I want to say, like 68 terabytes of storage. Yeah, it was just for data processing. So understanding things like its design, how it's configured, and its size is super critical. So let's talk about what RAID is. RAID is the redundant array of independent disks. It used to be called inexpensive disks, but now it's independent disks. The computer configuration involves 2 or more disks, and we have different types of RAID that we can work with. RAID 0 is a striping. They put half the data on 2 disks. This provides rapid access and increased storage, but there is no redundancy. If you lose one disk, you lose everything. RAID 1 is a mirrored copy. It's more for data recovery. If you lose one disk, you load off the second disk, it's 100% same copy. It's more expensive than RAID 0. I don't know how they get that. RAID 0 takes 2 disks, RAID 1 takes 2 disks. What you end up doing is you lose storage space. So for example, if you're doing RAID 0, you have 2 500 gig drives. RAID 0 will yield you 1 terabyte of storage. RAID 1, you have 1 500 gig drive, because again, both drives are duplicates of one another. So here we have, again, understanding RAID 0, RAID 1. RAID 0 is going to copy the data to both disks, but about half the data on each disk. That way, again, if you lose one disk, you lose the data. But again, it's faster access. Where RAID 1, you're going to copy 100% the same data to more than one disk. This gets really funny, because most people do not need to understand RAID 2, 3, 4, 7, 8. RAIDs 0, 1, and 5, and 6 are the common ones. But our book talks about it, so we'll talk about it. RAID 2 is similar to the RAID 1. Data is written to a disk on a bit level. Has better integrity than RAID 0, but it's slower than RAID 0. RAID 3 uses data striping and dedicated parity. RAID 4, data is written in blocks. Here is a nice example of, again, understanding RAID and how we do RAID 2. The better examples are going to be RAID 5 and RAID 6. RAID 5 is similar to RAID 0, and it places parity or a recovery portion on each disk. Thus, having one disk go down, you can recover it. But what happens when you have 5 disks and you're doing RAID 5 and you lose 2 disks? Well, RAID 5 is a little bit harder to recover from that. That's where RAID 6 comes into play. RAID 6, redundant parity on each disk, so that if we lose 2 disks, we're okay. RAID 10 is a combination of RAID 0 and 1, sometimes called RAID 1 plus 0, RAID 1.5, RAID 1 and 0. RAID 50 is a combination of RAID 5 and RAID 0. So you can actually take these base RAIDs and you can start combining them to get all kinds of numbers. Here we have RAID 5. Again, there's a parity portion on each drive. That way if a disk drive fails, we can recover. So now let's go back to the acquisition or acquiring RAID disks. Because the RAID disks are going to have very specific characteristics, we have to talk about what RAID is it? How much storage are we going to need for a disk image?
do we have the appropriate tool that can actually complete the acquisition? Can the tool read a forensics copy for a RAID image? That's been a huge thing because not all tools can do it. Because of the large file size, can we actually split the data on multiple disks? So kind of here copying a small RAID system in one large disk, it is possible, but if we're talking like a 10 terabyte array trying to be cloned to an 8 terabyte single disk, probably not going to happen. So we do have a few vendors that offer RAID acquisition functionality, ProDiscover and EnCase, as well as the AccessData FTK. Those are the big three. Exploit Forensics, Runtime Software, and our tools are also there. I've used ProDiscover, EnCase, and FTK for this functionality, so I know those features are there, and I know they work quite well. More often than not occasionally, but more often than not, modern day systems, the RAID system is too large for static acquisition. It's too much data, it's too large of a space. So we retrieve only the data relevant to our investigation with a sparse or logical acquisition method. Again, with things like increased storage, dedicated storage devices, RAID systems are getting way larger, so the concept of being able to do a RAID image is not commonplace anymore. I mean, you can still do it, but I mean, we're talking you have to have the appropriate sized storage easily. For example, even at home, I have 3 SANs. I have 1 SAN just for backup data. Sorry, my live data. Not backup, but just live data. Photos, videos, lectures, PowerPoints, TV shows, and it's 28 terabytes. And it's full. I have 2 backup SANs that handle just my backups. And that's just personal data. That's not anything work-related or business-related. So RAID systems are getting kind of larger.
So moving on, let's talk about the remote network application or acquisition type tools. You can remotely connect to a suspect's computer via a network connection, as long as you have the appropriate software. Drawbacks are things like firewalls, anti-spyware, anti-malware, firewalls, access control rules. Suspects could easily install their own security tools that then could trigger alarms to do specific functions. For example, if this is detected, do this. So there's some issues there. Common tools that actually do or allow for remote acquisition. ProDiscover allows for it. ProDiscover is fairly flexible. So it can capture volatile system state information. It can do analyzing and locating the appropriate files and processes. It can run hash comparisons. And it can create a hash inventory of all files remotely. Here's where we have to be, again, more careful. The appropriate write blockers need to be in place if we're not modifying any of the source data. This is where I have an issue with ProDiscover. Is if we're doing a remote acquisition, we have to install the remote agent on the suspect's computer so that we can access it. We have a ProDiscover server installation mode, which is a trusted CD, a pre-installation environment, and we can run it in stealth mode. Can change the process names to appear as an OS function for us to do this. But again, we have to install it, which by its nature manipulates the source disk. So that's why I have issues with that. But the remote connection security features, we can do things like encryption, password protection, signatures, things like that. A fun area for remote acquisition is we can actually integrate that with a common or a fairly decent IDS, or an intrusion detection system. So there are a lot of remote acquisition features that can be used. EnCase is, again, very flexible, but we have to understand some of the drawbacks for the remote acquisition. We have our tool in our studio. Here we have the remote connection using triple DES encryption. It can do a RAW. It can also support other various file systems. So there are some interesting tools here. US-LATT Pro. Again, it's an acquisition tool, similar to all the other acquisition tools. You just kind of have to figure out which one you're going to enjoy the most. ProDiscover and EnCase are what I've been used the most, so those are the ones that I normally teach with. But we also have things like F-response. Here, this is more of a vendor neutral, so that's kind of nice. There are different versions for F-response, so things like consultant, enterprise, tactical. So here we have different licenses, so that's kind of nice. One of the last things we have to talk about are other forensics acquisition tools. Things like iLook or SourceForge or PassMarks. PassMark software ImageUSB. On the fly, it's workable. PassMark does a acquisition tool. It allows us to do an ImageUSB for its OSF forensics analysis product. It works on modern day equipment, and you can download it. You can find fairly cheap licensing for it, but you have to read the appropriate terms and services to make sure that you have a legal copy. We have the ASRData SMART. This is a Linux forensics tool. Again, it can read bad sectors, it can mount drives, it can compress as required. So this is an interesting tool, but it's a Linux forensics tool, so you have to be a little bit more above average. Runtime Software. I've used this quite often for data recovery, but it's actually a shareware program. Licensing or donations are available. Works in RAW, segments, accesses, network drives. So this is kind of cool. I liked Runtime because it does access network computer drives. So that was kind of interesting because the forensics analysis or the data acquisition is allowed to leave that single workstation, or it's allowed to look at the network drives that are cached on that individual machine. So that was kind of interesting. We have iLook, pretty common with all the other items. SourceForge. This, again, several applications. I'm more weary of this one. But that's actually all that we had for our PowerPoint. Again, you want to make sure you understand the different types of formats, the acquisition methods, the different types of tools, what lossless is. Key concept here, always validate acquisitions. And understand the preferred acquisition tool and general what rate is. That's it for this chapter. I want to thank you.